Hi friends, welcome back to another video. In today's video we want to discuss more double integrals with polar coordinates. So we are going to be looking into how we can actually use the polar coordinates to take an integral. We kind of discussed the theory behind it in the last video, but today we really want to get into depth. So our example is going to be fairly straightforward. It's just going to be applying the theorems that we learned in the last video. We're going to go through a very similar structure that we did for general regions and rectangular regions, except now we're going to do circular regions and then general regions for polar coordinates. So now we're just going to try a circular region as our example. Now if you remember the conversion, if I have a region such that r is defined by r and theta, such that r is some positive number between a and b, and theta is some positive angle between alpha and beta, then we can say that the double integral over the region of a function of x and y with respect to a differential area element is equal to the integral between alpha and beta, and the integral between a and b of f of r cosine of theta, r sine of theta, r dr d theta. So as we can see, we've used our polar conversions, and then we used our polar differential element for our 2D integral, or for our double integral. Okay, so now what we're ready to do is we're ready to use this theorem in an example. So let's evaluate the integral where r is bounded by the circles with radii of 1 and 2 above y equals 0. So our integral that we want to evaluate is the integral over the region of 3x plus 4y squared dA. Now let's draw out our region. So if I have a xy plane, now it says we're going above y equals 0, so we're not going to have anything in the negative y, so nothing in quadrants 3 and 4, but we're bounded by circles with radii of 1 and 2. So here's a circle of radius 1. So a unit circle, or a unit semicircle. And then we also have a circle of radius 2. We're bounded by that as well. So this is our region. Our region is this, kind of half washer. Now, what we can do with this is use polar, because this would be very tricky to use rectangular. Obviously, we can't describe this as a type 1 or type 2 region, and it would be hard to divide it into a series of type 1 and type 2 regions. It's going to be much easier if we use polar coordinates, because these are circles, so naturally polar would be the way to go. So if we look at this, we can see that our radius would be between 1 and 2. We're going between radius of 1 here and radius of 2 there. And then theta, because we're dealing with a half semicircle, theta is going to sweep out between 0 and pi. So r is between 1 and 2, and theta is between 0 and pi. Now if we use our conversion such that x equals r cosine theta and y equals r sine theta, we can change our function of x and y into a function of r and theta. So 3x squared becomes 3r cosine of theta, and 4y squared becomes 4r squared sine squared of theta. Now we can plug this into our integral so that we have an integral between 0 and pi, an integral between 1 and 2 of 3r cosine theta plus 4r squared sine squared theta, r dr d theta. We'll distribute the r so that we have the integral between 0 and pi, integral between 1 and 2, of 3r squared cosine theta plus 4r cubed sine squared theta dr d theta. Now, taking this integral with respect to r is fairly easy. Polynomials, the trigonometric functions remain constant. So we get the integral between 0 and pi of r cubed cosine theta plus r to the 4th sine squared theta between 1 and 2 evaluated with respect to theta. So finally, we get the integral between 0 and pi of 7 cosine theta plus 15 sine squared theta d theta. The first term of this, 7 cosine theta, we can easily integrate. 15 sine squared theta, we need to use the half angle, or the double angle formula, so that we can change this into a double angle as opposed to a squared. So we get 7 sine theta plus 15 over 2 theta minus 15 over 4 sine 2 theta between 0 and pi, which is, of course, 15 pi over 2 once we evaluate the fundamental theorem of calculus. Now, really, the only new thing that we've done here is this conversion. This conversion in this step is really the tricky part that we've kind of needed to overcome in this example. The rest of it is fairly easy. It's just recognizing, hey, this function is over a circle. If it says literally a circle right there, you're going to know you want to transition into polar coordinates. Then you use the parameterizations here, the conversions, r cosine theta, r sine theta, to turn your function of x and y into a function of r and theta. And then you just integrate normally as you normally would, just remembering that r. This is so important, most people forget that there is an r there. So you just need to be very careful about putting our r's where they're supposed to be. All right, thanks for watching today's video. In the next video, we are going to do some examples with general polar regions, so integrating over like roses and limaçons and all of that fun stuff. So thanks for watching. We'll see you guys